Hello there and welcome back to the Science Sleepy Minds. Tonight, you're floating somewhere near the edge of the known universe, or at least the edge of what anyone claims to know. There's no sound here, of course, just the buzzing of particles you'll never meet. No lights either, except for the faint fading photons flung out 13 billion years ago. It's lonely, quiet, but not still. Because the universe is still expanding, still cooling, still playing out a story that, ironically, may never have had a beginning at all. You've heard it before, probably around grade school, the Big Bang. A single point of infinite density, a flash, then everything, the stars, the planets. You, listening to this, curled up in your blanket like a sentient noodle. But what if that whole bang thing is just a branding error? What if the universe didn't explode but slowly exhaled? What if it wasn't even a beginning, but a transition? So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know where you're tuning in from. Drop your city and local time in the comments below. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin, not at the beginning, but right in the middle of what feels like a very confusing story. That's the thing about origins. They're easy to romanticize, impossible to pin down. You've been told that everything started with a bang. But the truth is, the Big Bang wasn't so much an explosion in space as it was an expansion of space itself. Not a cosmic firework, but a sudden swelling of the fabric of reality, like someone dramatically inflating a cosmic souffle and then stepping back with jazz hands. And even the term Big Bang, it was actually a sarcastic jab. Fred Hoyle, a British astronomer who didn't believe the universe had a beginning, coined it during a BBC radio broadcast in the late 1940s, mostly to make fun of the idea. The name stuck. The universe, seemingly unbothered by branding critiques, kept expanding anyway. So, what did happen? Well, somewhere around 13.8 billion years ago, give or take a decimal you're too sleepy to care about, our universe went from a hot, dense state to a cooler, rapidly expanding one. But that's just when the universe as we know it began. It doesn't mean that's when everything began. Historians, cosmologists, still argue whether the Big Bang was a literal beginning or just a phase shift. You know, like puberty, but for the cosmos. Here's where it gets spicy. The closer we look at that beginning, the blurrier it becomes. You can't really see the Big Bang. What we observe is the cosmic microwave background radiation, a soft, staticky afterglow of the early universe, still buzzing around you, seeping through your Wi-Fi router and your microwave popcorn, whispering secrets from 380,000 years after the supposed bang. Before that, it's not just dark, it's unknowable. The laws of physics, as we currently understand them, simply break down when we try to rewind time past a certain point, specifically the Planck time, which is about 10 to the power of minus 43 seconds after the Big Bang. Before that, you might as well ask what's north of the North Pole. The question stops making sense. Still, we try. Some suggest that the universe may have emerged from a singularity, a point of infinite density and zero volume, which is science speak for, our math gave up, and now we're just hoping no one notices. Others, like Stephen Hawking, propose that there was no before the Big Bang, because time itself started with it. In that model, time is like a sphere, smooth and round without edges. Try to find the beginning of a circle. Go ahead, I'll wait. Actually, I won't because you're sleepy and this is not an exam. And yet, despite the complications, something happened. Because you're here, listening, existing, asking questions about origins like some kind of poetic sea cucumber even the ancients asked. Before telescopes and quantum fields, people tried to make sense of their sky with myths. In Babylonian lore, the world began with a chaotic ocean goddess being torn in half. In Hindu cosmology, the universe is endlessly created and destroyed by Vishnu's cosmic dance. And in Norse mythology, the universe emerges from the void Ginnungagap, which honestly just sounds like IKEA's most existential sofa. We've been searching for the beginning since we first looked up and noticed there was something to search for. But beginnings are slippery. They hide inside paradoxes, like this one. If the universe has a beginning, what caused it? But if it doesn't, how is it even here? There's also the cheeky first cause dilemma. If everything has a cause, what caused the first thing? And if something didn't have a cause? Why make that exception? God, quantum fluctuations, a four-dimensional loaf of bread sneezing in a higher realm. Quantum physics doesn't make it easier. In fact, it makes it weird. Because particles can pop into and out of existence seemingly from nothing. It's called quantum tunneling, and it happens more often than you change your socks. If something can come from nothing in a lab, maybe the entire universe is just an especially dramatic quantum burp. Fringe idea of the night. Some physicists have toyed with the idea that the Big Bang might have been the collision of two higher dimensional branes, short for membranes, in a grander 11-dimensional space. So yeah, you might be living in the echo of a cosmic slap fight. And of course, even the timeline is murky. Inflation theory, which we'll ease into in a later section, suggests that the universe underwent an absurdly fast exponential expansion in the tiniest fraction of a second after the Big Bang. But we have no clue what triggered that inflation, or what came before it. If you're starting to feel like the universe has commitment issues, you're not wrong. So maybe the Big Bang was real, but not the whole story. Maybe it was a beginning, but not the beginning. Or maybe it wasn't a beginning at all, but just a turning point, a phase shift, a line on a chart where everything started behaving differently. You blink, figuratively, and stars start to form, galaxies spin, atoms bond, and eventually someone invents cheese. All this unfolding from an origin we still can't quite define. But the question remains, if there was a beginning, why that one? And if not, if the universe has no beginning, how does anything make sense at all? Don't worry, it gets weirder. You're drifting now, not in a spaceship, not through stardust, but through the soft folds of very old ideas. Before anyone invented particle physics or wrote down the speed of light, people stared at the same stars you ignore on cloudy Tuesday nights, and they made up stories. Wild, brilliant, desperate stories. Because if you don't know what started everything, you might as well say it was a cosmic bird or an egg or a tree bigger than imagination. Long before equations, there were myths, and almost all of them had something to say about how the universe began. You're stepping now into a time when knowledge came wrapped in poetry, not proof. Don't worry, there's still wisdom in the weird. Let's start with eggs. The cosmic egg shows up all over the ancient world like an early universe Easter hunt. In Greek Orphic myth, the entire cosmos hatches from a silver egg laid in the deep. Inside, a primal being called Phanes, literally the one who appears. He bursts forth, dripping with potential, dragging existence behind him like confetti stuck to his foot. Meanwhile, in ancient Hindu tradition, you meet the Hiranyagarbha, the golden womb, or cosmic egg. It floats in the void until it cracks open to release Brahma, the creator god. And yes, the egg motif is suspiciously universal. You might even call it eggstra. Okay, that joke cracked under pressure. Let's move on. In Chinese mythology, the beginning is even messier. There's chaos, then a giant named Pangu hatches from, surprise, an egg. He separates yin and yang, forming the heavens and the earth, and holds them apart as he grows. When he dies, his body becomes the mountains, rivers and sky. Just your average deity-based terraforming. And over in Egypt, creation begins in a dark, watery abyss called Nu. Out of it rises Atum, the first god, standing on a mound of land that simply appears. No explosions, no drama. Just a calm, matter-of-fact surfacing from the nothing. Historians still argue whether these myths evolved independently, or if ideas migrated along early trade routes. But the uncanny similarities, eggs, voids, watery chaos, suggest we've always struggled with the same essential mystery. Why is there something instead of nothing? And does nothing even make sense? You're lying here now, probably half buried in your pillow. But imagine for a moment that you're an early human. No science, no telescope, no internet to yell at strangers, just night after night of darkness pierced by light. Stars that never stop moving. A moon that changes but never disappears. The urge to explain burns harder than any campfire. So you invent meaning. The sky becomes a dome. The earth floats on a turtle's back, or in some traditions, 4 elephants standing on the turtle, which to be fair sounds more structurally stable. These stories weren't wrong. They were just symbolic operating systems for minds that hadn't yet built radio telescopes. In the Norse cosmogony, things start with a void called Ginnungagap. Ice and fire meet in the middle. A primordial cow licks a salty block of ice until a god falls out. Yes, really, a cow. named Audumla. Historians still argue whether this was meant metaphorically or if Vikings just had a deep respect for dairy. And then there's the Mesopotamian myth of Marduk. In the Babylonian Enuma Elish, creation is an act of violence. Marduk slays the chaos goddess Tiamat and splits her body to form the heavens and the earth. It's visceral, brutal, and, frankly, very metal. The universe, born not in peace, but in blood and conquest. Here's the twist. Modern physics isn't all that different. The birth of the universe as we describe it now, violent, chaotic, pressurized beyond comprehension. Whether it's Tiamat being sliced or a quantum fluctuation igniting cosmic inflation, the theme remains: order from chaos, structure rising out of an unfathomable mess. Even the Abrahamic tradition, Genesis, gives you a kind of gentle poetry about beginnings. Let there be light, not a bang, but a word. Light drawn out from the void, separating day from night, heavens from earth. But even in that story, the formlessness is there first, the chaos, the deep. You never really escape it. And now, thousands of years later, you've swapped divine cows for cosmic microwave background radiation. You've traded myths for math. But the ache to know, that hasn't gone anywhere. Quirky tidbit for you. The Jain tradition in India doesn't even believe in a cosmic beginning. According to Jain cosmology, the universe is eternal and cyclical. No start, no end, just infinite loops. Think of it like the spiritual version of a loading screen that never quite finishes. So which is it? A singular moment of creation, an egg, a cow, a bang, or no beginning at all? Modern cosmology hasn't answered the question. It's just dressed it up in shinier math. We talk about singularities and quantum fields, but the truth is, the mystery remains. We've just gotten better at hiding it behind Greek letters. What's more comforting? A universe born in divine intent, or one that simply exists uninvited and unexplained? You shift slightly in bed, maybe reaching for your water, the room dim and humming. Outside, galaxies drift away from each other at increasing speed. You can't feel it, of course, but it's happening. All the time, the universe stretching out like taffy, just enough tension to hold everything in place, but always changing, always moving. Maybe these ancient myths weren't scientific, but they weren't stupid. They were metaphors for forces people didn't yet understand. And in a strange twist, some of their intuitions weren't that far off. The idea of cycles, of chaos, of something coming from the void. You're not that different from your ancestors, just better at Googling. The beginning, if there is one, is probably not going to be clean. It may not fit inside your tidy categories. It may never even be fully knowable. But the desire to tell stories about it, that's older than math, older than writing, older than language itself. You'll fall asleep tonight under the same sky they did, wondering, imagining, inventing. And maybe, just maybe, the universe likes it that way. You're reclining now, not in a temple or under a mythical tree, but in the quiet hum of a modern world built on equations, satellites, and data packets. If you squint past your own breath on a cold night, you might catch a star that's a few million years past its prime, its light finally landing on your lazy eyeballs. It's quaint. You staring up, it burning out. But someone once figured out that those lights were more than just poked holes in a velvet sky, that someone ironically didn't want the universe to have a beginning at all. Enter Albert Einstein, who unintentionally kicked off one of the most reluctant revolutions in cosmology. See, Einstein cooked up general relativity in 1915, a delicious equation-laden stew about how matter bends space-time. It explained gravity in a whole new way, far beyond Newton's falling apple and bonked heads. And hidden in Einstein's equations was a disturbing implication. The universe couldn't be static. It had to either expand or contract. But Einstein wasn't having any of that nonsense. The idea of a changing universe didn't sit well with him, so he introduced a fudge factor, a thing called the cosmological constant, basically to keep the universe from collapsing or ballooning. He forced the math to hold still. Later, he'd call that his greatest blunder, which, to be fair, is more charming than accidentally creating plutonium or something. Still, historians argue whether Einstein really saw the implications of his own equations. Was he too philosophically committed to a static universe? Or just reluctant to believe the math was outpacing intuition? Meanwhile, on the other side of the theoretical fence, a Belgian priest-physicist, because yes, that's a real combo, named Georges Lemaitre took Einstein's equations and said, "Wait, What if the universe actually is expanding? Lemaitre proposed that the universe began as a primeval atom, a single dense point that exploded outward. Basically, the Big Bang before it was cool. Einstein reportedly patted him on the head and said, "Your math is good, but your physics is abominable." That aged like expired yogurt. A few years later, Edwin Hubble came along and ruined everyone's denial. Using what was then state-of-the-art telescopic gear, Hubble observed that galaxies were moving away from us, and the farther they were, the faster they receded. It was like watching raisins zoom apart in a rising loaf of bread, assuming that bread was on fire and flung across an infinite void. This meant only one thing: the universe was expanding. You can imagine Einstein standing in the back of a conference room somewhere, dramatically clutching his metaphorical pearls. Because now, his equations not only allowed expansion, they demanded it. Lemaitre's primeval atom idea suddenly looked less like speculative theology and more like cutting-edge science. The Big Bang wasn't just theory, it was becoming the new model of reality. But here's the part they don't often mention in classrooms. Expansion doesn't mean galaxies are flying through space away from a central point. It means that space itself is stretching. The fabric of the universe is pulling apart like a cosmic yoga mat trying to achieve enlightenment. There's no center, no explosion point. Every point is receding from every other point. It's all moving, even you, though just barely. And not in a way that will help with your laundry pile. This revelation was huge. It suggested the universe had a beginning, or at least a starting condition. But as always, the more we learn, the more questions come crawling out of the quantum woodwork. Like this one. If the universe is expanding, what's it expanding into? You might imagine it like a balloon inflating in a big empty room. But in reality, the balloon is space. There's no room around it. It's not expanding into anything. It's just expanding. The edges aren't pushing out into a void because there is no outside. It's one of those ideas your brain politely tries to ignore for the sake of its own sanity. Still, this expansion model changed everything. It gave us a dynamic, evolving universe. One that had a hotter, denser past. One that might even end. But not everyone liked it. Back in the 1950s, Fred Hoyle, yes, the same guy who mocked the Big Bang name, still pushed for the steady-state theory, a model in which the universe had no beginning or end, but continuously created new matter to keep up with its expansion. So galaxies could fly apart all they wanted. New ones would just pop into existence between them. Infinite, eternal, never changing in density. Elegant? Maybe. Problematic? Definitely. Because the data didn't cooperate. The cosmic microwave background radiation, coming soon to a section near you, blew that steady-state theory into a fine dusting of disappointment. But even now, not everyone's convinced the Big Bang was a true beginning. Some propose it was a transitional event, just the latest reboot in an eternal series of universes. A bounce, a wrinkle, a really dramatic sneeze. Quirky side note, in 1927, Lemaitre published his expanding universe theory in a Belgian journal that no one outside of French-reading scientists noticed. 2 years later, Hubble announced his similar findings, and for decades got all the credit. Some now joke the Big Bang should be called the Lemaitre Bang, but I'll let you decide how catchy that is. Still, the foundation had been laid. Expansion is real, it's measurable, and it hints at something even deeper, that everything you see, the galaxies, the atoms in your tea, the phone lighting up your face in the dark, all of it was once packed into a space smaller than a grain of sand, maybe even smaller than that. You curl deeper into the blankets now, wondering how something can come from that kind of compressed absurdity. But then again, this whole situation, existence, time, thinking brains, IKEA, is kind of absurd, isn't it? Here's where the paradox begins to wrap itself in velvet. If the universe has a past and it's expanding, then it had to have been smaller, denser, hotter. Wind that clock backward far enough and you arrive at something different. A place where the laws of physics crumble into static. Where the math we trust throws its hands up and says, "I got nothing." Maybe that's a beginning, or maybe it's just where the next layer of the puzzle begins. You're still here, cozy, horizontal, probably weighing the pros and cons of rolling over, but the universe is anything but still. It's buzzing. Not loudly, mind you. It's more of a hush. A faint, nearly perfect static that hums through every corner of space like the universe is remembering a song it once knew but can't quite finish, and you can hear it. Not with your ears, but with the right equipment, and it's been doing this for billions of years. Let's talk about the cosmic microwave background, the CMB. It's the thermal echo of the early universe, the light left over from when everything was still a blinding soup of particles and photons tangled up in a high-energy wrestling match. This glow is the universe's baby picture, and unlike your baby pictures, this one hasn't been misplaced in a cardboard box or plastered with glitter by a well-meaning aunt. It's out there, all the time, around you, through you, on your skin, in your cereal, in your phone calls. Well, technically, about 1% of the static on an old-school TV screen is CMB noise. So if you've ever watched a channel with no signal and thought, "This is annoying," congratulations, you were witnessing ancient radiation from the dawn of time. Back in 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to get rid of a weird background hiss in their giant horn-shaped antenna. They thought it might be pigeon poop. Not a joke. They cleaned the equipment, they kicked out the pigeons, the hiss remained. Turns out they were listening to the afterglow of the Big Bang. Historians still argue whether they fully grasped the enormity of what they'd found. Meanwhile, a few miles away, another team of scientists had predicted this background radiation based on Big Bang theory. But Penzias and Wilson stumbled into the Nobel Prize anyway. Right place, right hiss. What makes the CMB so incredible is how boring it is. It's almost perfectly uniform, just 2.7 degrees above absolute zero. That's cold enough to make your freezer look like a sauna. But scattered across this cosmic wallpaper are tiny fluctuations, minute temperature differences that eventually gave rise to galaxies, stars, and your questionable taste in online purchases. Imagine the universe at that moment, roughly 380,000 years after the Big Bang. Still hot, still dense, but finally cool enough for atoms to form, for light to move freely. Before that, photons just bounced around in an opaque fog, trapped in a plasma soup. Then, snap, the fog clears, and light starts its 13.8 billion year road trip. And here's where things get weird, as if they haven't already. The CMB isn't just a relic, it's evidence. Concrete, observable proof that the universe really did begin in a hot, dense state. It's the smoking gun of cosmology, the static of a universe that's been talking to itself since it was a baby. But it also raises new questions. Those tiny fluctuations, they're suspiciously well behaved. Too uniform across regions of the sky that, by all logic, shouldn't have been able to communicate with each other. They were too far apart, moving too fast, and yet somehow ended up with matching temperature profiles like two distant cousins, showing up to a party in identical outfits. This is known as the horizon problem, and it's one of the reasons cosmologists turn to inflation theory, which we'll unpack later, don't worry. For now, just imagine the early universe expanding faster than the speed of light for a fraction of a second, smoothing everything out like a cosmic rolling pin. But back to the CMB fringe idea of the night. Some researchers once wondered if the CMB patterns could hide a message. Yes, like literal information, a message from the creator or from a previous universe. People actually scanned it for patterns, digits, anything unnatural. So far, just random fluctuations and beautiful noise. But hey, if the universe is a simulation, maybe the background radiation is the leftover loading screen. Still, those fluctuations gave us something huge, the seed data for how structure formed. Without them, no galaxies, no planets, no you. The tiniest temperature bumps created gravitational wells, little dips in the fabric of space that drew in matter and made things clump together. Basically, the universe used static to sculpt stars, which makes your morning bedhead seem slightly more poetic. You're curled up now, warm in a climate-controlled room, while 2.7 Kelvin photons drift silently through your walls. They're indifferent to your dreams and your deadlines. They've been on their way here since long before there was a here, before Earth, before galaxies had names, and you just intercepted them with your sleepy little brain. Kinda majestic, really. Now zoom out for a moment. Picture the entire observable universe, a 93 billion light-year-wide bubble filled with galaxies, black holes, gas clouds, and IKEA manuals. All of it soaked in this faint microwave background. That signal isn't just local, it's everywhere, a backdrop, a murmur, like the soft hiss of an old vinyl record behind the song of reality. It's even distorted slightly depending on where we move. The Earth orbits the Sun orbits the Milky Way, and the Milky Way moves through space, so we see a slight Doppler shift in the CMB depending on our motion. In a way, the universe gives us a frame of reference, a cosmic GPS anchor. But what came before this whisper? The CMB only shows us what the universe looked like after things calmed down. Before that, it's a blur, an opaque soup, a wall we can't see past. Cosmologists call this the surface of last scattering, which sounds like a fancy skincare serum, but actually refers to the moment photons could finally travel freely. Beyond that, we're blind, or at least nearsighted. We can infer, we can guess, but we can't see before it. And so, once again, the universe gives us a breadcrumb trail and then politely slams the door in our face. Thanks for visiting. Please enjoy your background radiation souvenir. But what a souvenir it is. That soft hum proves something massive happened. Something rapid. Something ancient. Whether it was the beginning or just a dramatic rebranding, we may never fully know. But the light from that moment is still bouncing around us, quietly illuminating the spaces between stars and the spaces between questions. So as you lie there now, listening, breathing, drifting further towards sleep, just know this: the sky is never really silent. The universe is still humming its birth song, and you're part of the echo. You're hovering now, not above Earth or inside some spaceship fantasy, but in the soft, curious fog of what came before. And that's where the trouble starts. Because tonight, you're not just poking at stars or tracing ancient radiation, you're poking at time itself, which for the record is not as straightforward as your wristwatch wants you to believe. Let's say this clearly. If the universe began with the Big Bang and time began with the universe, then what exactly does before even mean? This is the part where your brain pretends it's buffering. You grew up thinking of time as a line, past on the left, future on the right, and you, somewhere in the middle, scrolling steadily forward like the world's most dramatic progress bar. But that's not how the universe sees it. In fact, time is stitched together with space itself. Einstein's space-time isn't two things. It's one interwoven fabric, distorted by mass and energy. You move through both at once. The more you move through space, the slower you move through time. Go fast enough, say, near the speed of light, and time dilates. Pause for a second and realize you're basically a soft-serve cone with a physics engine. So if space and time are connected, then what does it mean for time to start? It's not like striking a match in the darkness. It's more like the match, the striker, and the concept of fire all popping into existence at the same moment. There wasn't time before the Big Bang, because there was no before. There was no timeline for things to happen on. It's like asking what's south of the South Pole. You've just run out of map. Stephen Hawking once said that asking what came before the Big Bang is like asking what's north of the North Pole. It's a meaningless question. Not wrong, not blasphemous, just linguistically cursed. But still, we ask. Historians, physicists, still argue whether time is fundamental or emergent. Is it a built-in feature of the universe, or is it something that appears once enough complexity arises, like consciousness or a fear of group chats? If time is emergent, then maybe before the Big Bang there was something, just not in any way we can measure or understand. A timeless quantum state, a mathematical abstraction, a kind of meta-reality lounging behind the curtain of causality, sipping vacuum energy and judging our calendar apps. Let's get weirder. There's a proposal in theoretical physics, bold and baffling, that says time might be imaginary. Not metaphorically, like time is a construct on a motivational mug. Literally imaginary, as in mathematically rooted in the square root of -1. In some models, including the famous Hartley-Hawking no-boundary proposal, the universe began not with a sharp point in time, but a smooth, rounded geometry, where time becomes space-like near the origin. No edges, no singular moment, just a gentle, curved beginning where time blends into existence like cream into coffee. And you thought bedtime was relaxing. Here's a quirky detour. In ancient Sanskrit philosophy, there's a concept called kalpa, a cosmic day in the life of Brahma, the creator god. One kalpa is about 4.32 billion years. After that, the universe dissolves into a temporary nothingness and then begins again. So even pre-science tradition suspected time might be cyclic. Not a line, but a wheel. And guess what? Some modern physicists are now considering the same idea, The cyclic model suggests that the universe didn't begin from nothing, but from the remnants of a previous universe. Time, in this model, didn't begin. It just passed through another transition. Big bang, big crunch, repeat forever, like the cosmic equivalent of laundry day. But not everyone buys it. Others argue time must have a direction. That entropy, the tendency of systems to move toward disorder, gives time its arrow. And if the universe started in a low entropy state, then time naturally flows toward higher entropy, toward disorder, toward, eventually, heat death. Sleep tight. Still, you can't ignore the possibility that our sense of time is just wrong, that it's a useful illusion generated by consciousness, that the past and future already exist, fully formed, and we're just moving through them like a needle pulling thread through a static quilt. This idea, called the block universe, treats time as a dimension like space. All moments are equally real. All events, birthdays, supernovas, your most embarrassing email, are eternally fixed in a four-dimensional loaf of reality. You don't create the future, you just encounter it. It's unsettling, but also kind of comforting. Like you're not lost, you're just scheduled. But what if there was never a start at all? There's a theory gaining traction that says the universe may be past eternal, always existing, never beginning. In this model, time stretches backward infinitely. The Big Bang wasn't the beginning, but just the start of our observable section, a particularly spicy chapter in a much longer book. And if time is infinite, then somewhere in that vast ocean of moments, anything that can happen will, including you, multiple times, with slightly different socks. Now bring it back to you, still curled up, maybe slowly blinking, maybe questioning your life decisions. You exist inside time. You can't step out of it. You feel it pass, but you can't see it. You can't touch it. And yet your entire life is shaped by it. You age. You remember. You hope. But none of that proves time is real. It just proves it's real to us. Kind of like how dreams feel true until you wake up. Maybe time too is a dream the universe is having, or a scaffolding it used to build itself, and will one day discard. If that's true, then the beginning we're looking for? It may not be a moment. It might not be anything at all. It could be a transition in the rules, a shift in how the universe plays the game. Or maybe, and here's the gentle shrug of theoretical physics, it just is. No cause, no before, just the raw, unfiltered fact of existing, like your favourite weird uncle who shows up to every party but never explains where he came from. So what's the answer? Did the universe have a beginning? Or did time simply start when it had nothing better to do? We don't know, but we keep asking. And the asking might be the point. You're shrinking now, not physically of course, unless your blanket has suddenly gained sentience and decided to crush you gently. But conceptually, you're falling down into the smallest possible scale your imagination allows, past atoms, past electrons, into a realm where the difference between something and nothing blurs until it's not even clear which one you're dealing with. Welcome to the quantum vacuum, a place where empty doesn't mean what you think it means. Let's get one thing out of the way. When physicists talk about nothing, they don't mean nothing. Not the kind of nothing you imagine when you think about a blank canvas, or the awkward silence in a group chat after you say vibe check. They mean a vacuum state, a field buzzing with possibility, a restless emptiness filled with jittery fluctuations that can and do occasionally burp something into existence. Yes, you heard that right. Even in its most stripped-down form, space is never truly still. Even at absolute zero, where all classical motion should stop, quantum fields keep flickering. Virtual particles spontaneously appear and disappear, borrowing energy from the vacuum like impatient kids sneaking cookies before dinner. This is called zero-point energy, and it's why even nothing is something. It's also the reason some theories suggest that our entire universe might have emerged from a quantum fluctuation. Imagine it. You're lying in bed, and somewhere, in some infinitesimal speck of space-time, a blip occurs. That blip inflates, grows, cools, forms atoms, galaxies, late-night snack cravings, and here we are. All from what appears, on the surface, to be the ultimate magic trick, pulling everything out of nothing. Now, before you throw your pillow across the room in frustration, let's clear something up. This isn't magic, it's quantum physics, which to be fair is only slightly less confusing. The quantum vacuum isn't like the vacuum of space. It's a seething foam of uncertainty, filled with fleeting bits of matter and energy that don't last long enough to break any laws. This chaos is baked into the universe's code, like a digital glitch that somehow became a feature. We see the effects of these fluctuations everywhere. In the Casimir effect, two uncharged metal plates placed extremely close together in a vacuum will feel a mysterious force pulling them together, not because of gravity but because quantum fluctuations in the vacuum are pressing on them. Space, quite literally, is never empty. It's like the universe has a built-in white noise generator running in the background at all times. Fringe theory of the evening? Some cosmologists speculate that this quantum froth could spawn not just particles, but entire baby universes. Each fluctuation, under the right conditions, could inflate into a full-fledged cosmos. Ours might just be one bubble in an endless fizz of universes, a carbonated multiverse, if you will. But wait, it gets even stranger. In quantum mechanics, the uncertainty principle means you can't simultaneously know both the position and momentum of a particle with perfect accuracy. This isn't just a matter of measurement. This fuzziness is built into reality itself. At tiny scales, the universe doesn't behave like a smooth clockwork machine. It's more like jazz, improvised, probabilistic, a little unruly. Now apply that logic to the early universe. When it was smaller than a proton, quantum effects weren't just important, they were everything. Gravity, space, time, none of it acted the way you're used to. There were no atoms, no forces as we know them, no before or after. Just a jittering froth of potential. That's where quantum cosmology comes in. It tries to explain how this wild subatomic soup could give rise to the structured, expanding universe we observe. And it often involves marrying two awkwardly incompatible theories, general relativity and quantum mechanics. Kind of like trying to merge a poetry reading with a monster truck rally, and they hate each other. General relativity is smooth and elegant. It describes the vast, curved fabric of space-time. Quantum mechanics is messy and twitchy, focused on the unpredictable behaviours of tiny particles. Neither likes playing in the other's sandbox, and yet, if you're going to understand the true beginning of the universe, if it even has one, you need both. That's the Holy Grail, a theory of quantum gravity. We don't have it yet, but we're trying. One approach is to quantize gravity directly, which is like trying to put a leash on fog. Another path leads to string theory, which suggests that particles are actually tiny vibrating strings, existing in more than the three dimensions you know and love. Others turn to loop quantum gravity, which we'll dive into later, where space itself is made of discrete loops, little chunks instead of smooth fabric. But whatever the approach, they all have to deal with the wild card at the centre of everything, the quantum vacuum. Because if the universe can emerge from a fluctuation in the vacuum, then the question changes. You no longer ask, what came before the universe? You ask, what are the rules that allow universes to emerge from nothing? And more disturbingly, why do those rules exist in the first place? Historians still argue whether this counts as a satisfying answer. Some say yes. A quantum vacuum obeys laws, and those laws allow for spontaneous creation. Others ask, where did the laws come from? Are they eternal? Are they part of a bigger framework? Are we inside a cosmic sandbox coded by something else entirely? You pull the covers tighter now, because the deeper we go, the less it feels like we're asking about beginnings, and the more it feels like we're asking why anything exists at all. Let's not forget the Boltzmann brane scenario, a fringe idea so unsettling it should come with a blanket warning. In an infinite, eternal vacuum, with random quantum fluctuations happening forever, it's statistically more likely for a disembodied brain with false memories of the universe to pop into existence than for an entire fine-tuned cosmos to appear. Yes, according to that logic, you could be a brief flicker of awareness in a sea of nothingness, hallucinating this bedtime story, the stars, your cat, and your last birthday. Probably not, but sleep well. Here's the gentler takeaway. If the vacuum can create, then maybe nothing is never really nothing. Maybe what we think of as emptiness is the most fertile field of all. Maybe the universe began not from absence but from possibility, the default condition of existence itself. Or maybe the vacuum is just what the universe falls back to when it's not busy being loud. Either way, the quantum realm doesn't care what you believe. It just hums along, flickering, jittering, burping reality into being like it's trying to win a bet with causality. And you're riding that wave, curled in your bed, afloat in the vacuum sea, waiting for the next fluctuation, Or maybe being one. You're breathing slowly now, your thoughts softened at the edges, lulled by radiation, relativity, and the faintly ridiculous idea that everything began from a burp in the vacuum. But what if that burp wasn't the first? What if the universe didn't just pop into being once and for all, but has been pulsing, stretching, collapsing, and restarting forever? Tonight you're caught in the rhythm of the cyclic universe, a cosmic heartbeat, a loop so vast you can't feel its pulse, yet somehow you're part of it. Let's start with the simplest idea. Maybe the Big Bang wasn't a beginning, but a bounce. Instead of the universe exploding out of nothing, it might have been rebounding from a previous contraction. That's right. Imagine a universe that expanded, slowed down, reversed, collapsed in on itself, and then bounced outward again into the universe you're lying in now. You're not living in the first universe. You're living in the latest round. Historians still argue whether early Indian and Greek cosmologies hinted at this, but the idea of an eternal cycle isn't new. It's older than modern physics. The ancient Stoics, for example, believed in a cosmos that burned itself down in a great fire, an ekpyrosis, only to be reborn again and again in infinite repetition. Total drama queen energy, honestly. And now, some modern physicists are wondering if the Stoics might have accidentally stumbled onto something useful. The cyclic model re-emerged in the early 2000s, championed by scientists like Paul Steinhardt and Neil Turok. Their version builds on the idea of branes, as in membranes, big, multi-dimensional surfaces floating in a higher dimensional space. In their model, our universe is one such brane. Every so often it smashes into another brane, and the resulting collision is the Big Bang. Not an explosion of matter from a point, but the transfer of energy from one brane to another, like cosmic slapstick. And then, predictably, the universe expands, evolves, ages, and begins its slow slide back inward, setting up the next bounce. Over and over, no beginning, no final end, just an endless oscillation. Boom, crunch, boom again, like breathing, but on a timescale so vast it makes geological epochs look like speed dating. But can the universe really do that? It depends who you ask, and how much math you're willing to tolerate before giving up and making tea. The biggest problem with a cyclic universe has always been entropy. Remember that thing about disorder always increasing over time? Well, if the universe has been cycling forever, each bounce should get messier and messier. Eventually, you'd end up with a universe so bloated and boring it couldn't bounce back. It'd just sort of sigh itself into permanent heat death. But new models try to cheat entropy by resetting conditions at each bounce. Think of it like clearing your browser history and pretending you're a brand new user. Except instead of cookies and autofill data, you're resetting quantum fields and spatial curvature. It's clever, it's elegant, and it might even work. But not everyone's convinced. Some cosmologists argue that the bounce model requires some pretty fancy tweaks to general relativity. Others point out that we still haven't figured out how to describe what happens at the bounce, the exact moment of reversal, where contraction becomes expansion. Our math gets fuzzy there, real fuzzy, as in our laws of physics kind of explode fuzzy. Still, the bounce idea solves some lingering problems. It explains why the universe looks so smooth and flat. It provides an alternative to inflation theory, which we'll be diving into soon, and maybe most intriguingly, it sidesteps the awkward question of what came before the Big Bang. Because in a cyclic model, the answer is another universe. There's something deeply satisfying about that, isn't there? No abrupt beginning. No need for a first cause, just an eternal rhythm. And if the cycle is truly infinite, then every possible configuration of matter has happened before and will happen again. Yes, including you. Listening to this, in bed, hearing these exact words, 1 billion cycles ago and 1 billion cycles from now. Cue existential vertigo. Let's pause for a quirky side story. In the 1930s, physicist Richard Tolman proposed an early version of the cyclic universe. He thought maybe the universe could collapse and re-expand indefinitely. He even tried to account for entropy, suggesting that the cycles might get longer each time but still continue. Sadly, the idea didn't catch on, mostly because we lack the observations to support it. But the idea never really died. It just took a nap, a long cosmic nap. And now, as modern physics struggles with the sharp edges of the singularity at the Big Bang, cyclic models are once again whispering, hey, what if we've done this before? Some even suggest a kind of phoenix universe, one that ends in a kind of cosmic rebirth, where the very fabric of space and time is recycled, refreshed, and released anew. Nothing is truly lost, only transformed. Of course, there's a trade-off. In a cyclic universe, there's no true beginning, but there's also no final answer, no grand climax, no big reveal where a cosmic narrator turns and says, "Here's why it all happened." You just keep going. A new game each round, no memory of the last, no end credits, just patterns, evolution, collapse, bounce. And you're just a ripple on this current loop, a moment in the breath. Still, there's comfort in repetition, in knowing the universe has done this before, that it might do it again, and that maybe, just maybe, everything you do, think, and feel isn't some random blip in a meaningless void, but part of a pattern so vast it wraps around itself. Whether we're in the first cycle or the 10 billionth doesn't change the fact that you exist now. You're a warm cluster of improbable atoms listening to an even more improbable explanation of an infinite breath. And maybe, somewhere in the far future after this universe collapses and bounces again, another version of you will ask the same question. Did it begin, or did it bounce? You're still floating, but now you're starting to feel the edges of space bend, twist, maybe even dissolve a little. Because tonight's descent isn't just deep, it's extra-dimensional. You're slipping sideways now, through something called the brane world, where space isn't just the empty stage, it's possibly the illusion. Let's be honest, 3 dimensions plus time already feels like a lot to handle. You can barely navigate a parking garage without internal GPS failure, and now we're talking about 10, maybe 11 dimensions. Don't worry, you don't need to see them, in fact you can't, but that doesn't mean they aren't there. First, a little grounding. In string theory, one of the leading and most mind-bending attempts to unify all the fundamental forces, everything in the universe is made not of point-like particles, but of tiny vibrating strings. Each string's vibration determines what kind of particle it appears to be, an electron, a quark, or something even stranger. Here's the catch. String theory only makes sense if you assume the universe has more than 4 dimensions. Specifically, 10 spatial dimensions and 1 time dimension. But don't panic. The extra ones are curled up, compactified as they say, in unimaginably small shapes called Calabi-Yau manifolds. They're so small you'll never notice them. They're like the fold in your bedsheet you never realise you're sleeping on. But what if some of those extra dimensions are bigger than we thought? This is where brane theory, short for membrane, comes in. It suggests that our entire universe might be a 3-dimensional brane floating inside a higher dimensional space called the bulk. You can think of it like this. You're living on a cosmic sheet of paper, but the paper itself is drifting in a room with extra directions you can't see. What's in the bulk? Maybe gravity, maybe other branes, maybe entire other universes completely invisible to us, stacked like pancakes in a dimension we'll never touch. Historians still argue whether these ideas are testable or just beautiful math, but the implications are huge, and not just metaphorically. For instance, one of the puzzles in physics is why gravity is so much weaker than the other forces. Your fridge magnet can overpower the entire planet's gravitational pull, and that's not just because it's judging you. Some physicists think gravity might actually be leaking into extra dimensions, diluted across the bulk, while the other forces are confined to our brane. It's like gravity has a side hustle in a dimension we can't perceive. That's why these theories matter. They don't just sound cool, they try to solve real problems. But things get wilder when you ask, what happens when branes interact? Some models propose that the Big Bang wasn't a one-time miracle, but the result of 2 branes colliding in the bulk. Imagine 2 vast sheets of cosmic paper drifting toward each other. When they touch, bang, energy is released. A new universe is born. Sound familiar? This is the basis for the ekpyrotic universe model, which we brushed against earlier. In this version, branes periodically bump into each other, triggering cosmic cycles of expansion and contraction. It's not so much a birth as it is a reboot, a cosmic fender bender that leads to reality itself. Fringe idea of the night? If our brane is floating in the bulk and other branes exist, could someone else be living on one of them? It's not science fiction, at least not entirely. The idea of a parallel universe isn't just a multiverse gimmick, it's baked into some versions of brane theory. These aren't just parallel in the sense of being alternate timelines. They're physically real, neighbouring universes separated from us by an unfathomably thin dimensional gap. We wouldn't see them, we wouldn't interact, Unless, of course, gravity manages to tunnel across that boundary. And if it can, then maybe we could detect its effects. Maybe those little ripples in space-time we measure, gravitational waves, aren't all from colliding black holes in our universe. Maybe some of them are echoes from across the dimensional divide. Cue your neck hairs standing up. There's something eerie about this idea, that we might be floating next to entire realms we can never touch. That reality is just our slice of a much thicker, layered cake. And that somewhere, somehow, a version of physics slightly different from ours might be playing out on another brane, quietly, invisibly, next door. And here's a thought to fall asleep to. If branes can drift, collide, and ripple, then so can we. Some theories suggest that the geometry of our brain determines the properties of reality itself. Change that geometry, warp it, stretch it, bend it, and everything changes. The laws of nature, the speed of light, the rate at which stars burn and atoms cling together, which means maybe universes don't just pop into existence, maybe they tune into existence, like chords struck on a multidimensional instrument, different vibrations, different realities. You're lying there now, still, quiet, grounded in 3 familiar dimensions. But somewhere, mathematically speaking, you might be stretched across 7 others. Compact, folded, unreachable. They don't affect your dreams, but they might be the reason your atoms even exist. Quirky side note, in some versions of these theories, the shape of the extra dimensions determines everything from particle masses to the fundamental constants of nature. Change the shape, change the rules. In that sense, you owe your existence to the topological quirks of curled-up spaces you'll never visit. So no pressure. Whether these ideas are true, or just math stretching its legs, is still up for debate. Some physicists love brane theory. Others roll their eyes and ask for evidence. The experiments required to detect extra dimensions, if they exist, would need energy levels far beyond what we can currently produce. Even the Large Hadron Collider, with all its hypermagnets, can't pierce that veil. Not yet. Still, the math holds, the models work, and the questions remain. What if the Big Bang wasn't a beginning? What if it was just a touch? A contact point between higher dimensional objects? What if you're a shadow, projected onto a lower dimensional surface, living in a universe that is itself a kind of hologram? Yes, we're going there soon. But not just yet. For now, just let this thought sink in. The universe may be bigger, not in size but in structure, than you ever imagined. And the beginning you've been searching for? It might be drifting just out of reach, on a surface that's rubbing shoulders with infinity. You're pacing the edge now, metaphorically of course, because the floor beneath your thoughts just got suspiciously slippery. Tonight, you're standing in the celestial version of a mega mall with infinite floors, a reality warehouse, a cosmic filing cabinet that never ends. And somewhere in this vast, possibly imaginary archive, there's a version of you asking this same question, and probably a version wearing Crocs. Welcome to the multiverse, the theoretical realm where the universe you know is just one of countless others, each with its own rules, constants, dimensions, and mood lighting. It starts innocently enough. Imagine our universe as a bubble. Now imagine that it's not alone, that there are more bubbles, some nearly identical to ours, others wildly different. A few might be entirely made of helium or dark energy. One might have never formed stars, another might have invented pineapple pizza before inventing fire. Some models suggest the multiverse is infinite, not big, not really big, infinite. A number so large your brain has to file it under sure why not and move on. The concept isn't just whimsical, it's a serious proposal in several branches of modern physics. Let's start with eternal inflation. Remember inflation, the idea that the early universe underwent a rapid, faster-than-light expansion just after the Big Bang? Well, some models of inflation suggest it never really stopped. It just slowed down in our region, allowing galaxies and stars to form. But elsewhere, inflation kept going. Like cosmic popcorn kernels popping endlessly in a quantum microwave. Each pop becomes its own universe, its own bubble, completely disconnected from ours, drifting in a sea of inflationary space. We happen to live in one of the calmer bubbles, lucky us. But here's the twist. If eternal inflation is real, then universes are being born constantly. Right now, somewhere. Like a metaphysical assembly line churning out realities in bulk. Historians, cosmologists, still argue whether these multiverse models are testable or even meaningful. Some see them as elegant extensions of inflation theory. Others say it's just metaphysical fan fiction, unless you can prove any of those other universes exist. But let's not stop at inflation. Oh no, quantum mechanics has its own brand of multiverse, the many worlds interpretation. This one says that every time a quantum event could go more than one way, say, a particle spins left or right, the universe splits. One copy sees left, one sees right. Every quantum choice branches reality into multiple paths. So when you chose tea over coffee this morning, another you went with the coffee, and probably regretted it. Every decision, every probability, every roll of the dice spawns a new universe, an endlessly branching tree of what-ifs. The universe, it seems, is indecisive, and compensates by trying all the options, which means, in this view, you're not unique. You're just one node in an endless lattice of selves, each diverging at every crossroads. Somewhere, another you became a dentist. Somewhere else, you never heard of this video and are watching otter compilations instead. Now, whether those other yous are physically real or just mathematical possibilities is the real debate. Some physicists embrace the idea. Others say it's a philosophical dead end. Because if you can't ever interact with those other branches, can they be said to exist? Then again, when was the last time you interacted with Neptune? Still there though. Then there's string theory's multiverse. In some versions, the theory allows for an absurd number of possible vacuum states, 10 to the power of 500 or more. That's one followed by 500 zeros, a number so large it makes your student loan look charming. Each vacuum configuration corresponds to a different possible universe, with different values for the physical constants: speed of light, strength of gravity, charge of an electron, all up for grabs. So out of this mind-numbing cosmic menu, we got this version. Why? Well, here's where the anthropic principle crashes the party. It says, we live in this particular universe because it allows beings like us to exist and ask these questions. Out of the vast ocean of possibilities, we find ourselves in a universe with just the right ingredients. Not because it's the best, but because it's the only one where anyone's around to notice. It's like waking up in a hotel room and thinking, yeah, wow, this place has beds, electricity, and running water. Must be designed just for me, when in fact, you're only in that room because the ones with no air or solid flooring killed off their guests long ago. Fringe idea of the night. Some theories suggest the entire multiverse is embedded in mathematics itself, that all logically consistent mathematical structures exist somewhere, and each one corresponds to a real universe. You don't live in the universe, you live in math, which would explain why your taxes feel like a cosmic punishment. But let's get personal, because there's something deeply weird, almost spiritual about multiverse thinking. It both humbles and unsettles. On one hand, it says you're not alone. There are versions of you everywhere. You made all the other choices. You kissed the other person. You went to the other city. You failed. You succeeded. All of it. On the other hand, it forces you to ask, if everything happens somewhere, what really matters? Does it make your choices meaningless or more precious because this version of you made these choices? And deeper still, if all beginnings are constantly beginning somewhere, then did the universe ever start at all? Or are we just a sliver of an eternal bubbling cosmos? No beginning, no end, just endless variations. You roll over. The room is quiet. The fan hums like background radiation. Somewhere, in another bubble, another you is staring into the sky and wondering the same thing. Somewhere else, a universe formed with different constants, and stars never ignited. And somewhere, the multiverse clerk, who's definitely underpaid, is trying to file every version of you alphabetically. The irony, of course, is that we may never be able to detect any of it. The multiverse might exist entirely beyond our observable horizon. It might be real and unreachable, or it might be just a clever way of avoiding hard questions about why our universe turned out the way it did. But tonight, for this brief moment, let yourself drift through the corridors of infinite possibility, through bubbles, branches, brains, and breath. And remember, if this is just one universe among many, it's still yours. You're weightless now, not just because you're half asleep and halfway through the cosmos, but because tonight's idea might dissolve the very notion of direction, of flow, of forward. Because now we ask, what if the universe doesn't begin, doesn't end, and doesn't move, because it's already all there? Welcome to the unnervingly still world of the block universe. Here, time isn't a river, it's a landscape. You're used to thinking of time as passing, moments clicking forward like the world's slowest slideshow. But in this view, all moments, past, present, and future, are equally real. They don't happen one after the other. They exist all at once, stacked like pages in a book or slices in a cosmic lasagna. You're not travelling through time, you're a fixed creature in a four-dimensional loaf. Your life a shimmering thread already woven into the fabric of space-time. This idea comes from Einstein's own equations. Yes, we're dragging him back in. When general relativity describes space-time, it doesn't single out the present moment. There's no cosmic now in the math. Time, like space, is just another dimension. Your birth, your next sneeze, and the sun's eventual death are all coordinates in this unchanging whole. And yes, it feels deeply wrong. Because you experience time passing, you feel change, you remember yesterday and worry about tomorrow. But in the block universe, that's just part of the illusion. Consciousness gives you a moving spotlight, like a torch sweeping across a dark painting. But the painting, the whole thing, is already finished. So if that's true, what does it mean for the idea of a beginning? Well, in a block universe, the Big Bang is simply one location in space-time. It's not a starting line, it's just where the loaf happens to be hottest and most compressed. And your questions about what came before might be like asking what's north of the North Pole. Again, the beginning isn't before, it's just a slice you haven't wandered across yet. Historians still argue whether this model truly solves anything, or just reframes the problem in more poetic terms. But it's hard to ignore that Einstein himself hinted at this view. In a 1955 letter, mourning the death of a friend, he wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. Let that sink in. The guy who gave us E equals mc squared believed time might not be real in the way we experience it. And here's where things get properly strange. If all of time already exists, then everything that has happened always happens. Nothing is truly caused. It just is. The block universe doesn't evolve, it simply is. That means your life isn't unfolding, it's encoded. Like a DVD that contains the whole story, even if you're currently paused at chapter 4, rewinding because you missed the part where you forgot to do laundry. Again, quirky thought. This perspective weirdly aligns with some philosophical idealism, the notion that reality is fundamentally mental or informational. If your conscious experience is just a tour through a fixed four-dimensional landscape, maybe your mind is like a cursor scrolling through an already rendered program. Reality is playback. Now pause, breathe. This doesn't mean your choices are meaningless, it means your choices are part of the block, just like your height or your favourite soup. They exist. You're not trapped. You're crystallized. And you're you all the way through, from your first gummy smile to your last dramatic sigh. Still, the implications are deep. If time doesn't pass, if it just is, then maybe asking when the universe began is like asking where the edge of space is. You're assuming there's a boundary when there might just be more fabric, curved, warped, looping back on itself in ways your instincts can't grasp. There's another twist here. The block universe challenges not just beginnings, but causality. If every event is fixed, then cause and effect are just relationships between different locations in space-time. Like how your living room connects to your kitchen. One didn't cause the other, they just exist next to each other. So maybe the Big Bang didn't create everything, it's just where everything starts happening. Fringe theory of the night? Some physicists and philosophers argue that we could, in principle, experience time in reverse if our brains were wired differently. The universe doesn't actually distinguish between forward and backward in time at the deepest level. Only the arrow of entropy gives us a direction. If our mental processes somehow operated in the other direction, you might remember the future and anticipate the past. It sounds absurd, but thermodynamically, it checks out. So what does that mean for you drifting here halfway to dreamland? It means the question, when did the universe begin, might be based on a flawed metaphor. There may not be a when. The universe didn't begin, and it won't end. It simply is, in its entirety, timeless and whole. And in that view, every version of you, every second you've ever lived or will live, already exists, eternally. You, laughing with your friends, you, falling in love, you, wondering where you put your keys, all of it, still there, still happening, not moving, just being. Quirky callback time. Remember that Egyptian god Atum we met earlier? The one who rose from the chaos and just was? Maybe he had it right. Maybe existence doesn't need a trigger. Maybe being is enough. And maybe if we squint at the universe the right way, not as an explosion or a ripple or a simulation, but as a block, a sculpture beyond time, then the search for a beginning becomes something else entirely. Or it becomes a meditation, not what happened first, but what is always true. And maybe that's the real bedtime story. Not a bang, not a bounce, not a flash, but a stillness so complete, so vast, that motion itself becomes illusion. And time, as we know it, dissolves into a kind of eternal now. So here you are frozen in the block. And it's okay, you don't have to go anywhere. You're already everywhere you'll ever be. You're blinking slowly now, your thoughts wrapped in space-time like warm dough in a cosmic croissant. But just as you are starting to accept the idea of being a frozen moment in an eternal loaf, things take a sudden twist because tonight the math gets funny, literally. You're stepping into a realm where equations use imaginary numbers to describe reality, where time can turn sideways, and where causality, the beloved this leads to that, might not be fundamental at all. Welcome to the strange mathematics that may be holding the universe together, or pulling it apart. Let's talk about imaginary time. Yes, it sounds like something from a sci-fi novella your cousin insists is actually really deep, but it's a real concept from physics. In imaginary time, the time dimension is treated as a spatial one. You rotate it 90 degrees in the complex plane. Yes, that complex plane, the one from high school math you pretended to understand. Imaginary time replaces t with it, not it, like the clown, calm down, meaning it uses the square root of -1, usually represented as I, to make time behave like space. Suddenly, time isn't a forward arrow anymore. It becomes a direction you can walk in, like length or width. Stephen Hawking and James Hartle use this trick in their no-boundary proposal, a model where the universe doesn't have a sharp origin point, but instead curves smoothly into existence. No singularity, no edge. Just a round off at the start, like the South Pole of the Earth. Not a beginning, just a place where other directions lose meaning. Historians still argue whether this mathematical maneuver is describing something real, or just a way to avoid dealing with the Big Bang's annoying singularity problem. But the result is seductive. A universe that doesn't need a beginning, because the question itself doesn't apply in imaginary time. It's like asking when the circle starts. You're still asking for a first point on a thing that doesn't have one. Let's zoom in a little further because this is where reality starts leaking logic. In normal time, we're bound by causality. A causes be, you put toast in the toaster and then it gets toasted. You don't expect it to pop up golden brown before you push the lever. But in certain models of quantum gravity, causality might not be a fundamental part of the universe. It could be emergent, like temperature, or your interest in finishing a book you've already watched the movie for. And in imaginary time, the usual constraints that define cause and effect go fuzzy. Events aren't strictly chained together. They're more like features on a terrain. You don't move through them. You observe them from different angles. It's deeply weird and deeply mathy. But here's the thing. Some of the most powerful physics tools we have rely on this kind of strange mathematics. For example, in quantum field theory, we often use imaginary time when performing complex integrals. It's cleaner, it behaves better, and it allows certain infinities to cancel out, like cosmic customer service waiving your late fee. Quirky fact of the night. Physicists working on black holes and thermodynamics found that when they calculate things like Hawking radiation, switching to imaginary time turns black holes into spheres, which is hilarious, terrifying, and weirdly elegant. But let's return to the beginning. Why does any of this matter? Because the moment you allow time to be imaginary, even just as a mathematical trick, you crack open the idea that time might not be what you think it is. It might not be linear. It might not flow. It might not even be real in the way space is. In fact, there are some physicists who believe time isn't fundamental at all. They suggest that the universe is described entirely by relations, between objects, between events, and that time is something we infer, not something that actually exists. You see change. You remember past moments. But that might be just how your brain stitches the world together. Time, in this view, is a cognitive illusion, like depth in a flat painting or plot in a very long dream. fringe idea of the night. There's a theory called causal set theory, which says space-time isn't smooth and continuous, but made of discrete events, a kind of cosmic dot-to-dot. Each event has a before and after, but only in a local limited sense. The big picture, it's a mess of nodes connected by causality, but without a smooth timeline. You might think of time as a string. Causal set theory sees it more like a scatterplot, where order is inferred by relationships, not imposed by clocks. And then there's retrocausality, the idea that events in the future might influence the past, not in a send an email to 1997 way, but in subtle quantum experiments where particles seem to know what measurement you're going to do and behave accordingly. It's real, it's tested, and it breaks the part of your brain that likes cause and effect to behave politely. So what does this all mean for the beginning? Well, if time is not fundamental, then maybe the universe doesn't need a beginning. Maybe the entire concept is a misunderstanding, like thinking a rainbow has a start or that your dreams happen in real time. Maybe time emerges after certain conditions arise, like space-time geometry reaching a certain threshold, or the universe cooling enough for causality to make sense. In that case, the universe wouldn't have a first moment the way a film has a first frame. It would have a threshold, a phase transition. Before that, not nothing, just no time. And suddenly you're not asking what came before the Big Bang, but when did when become a thing? Now that's a sentence. So here you are, half melted into your blanket, being told that time might be a mathematical illusion, that imaginary numbers might hold the key to why the universe doesn't tear itself apart, that your life might not be a string of moments but a network of relations, like constellations traced on the night sky. There's no reason to panic, no need to feel lost. If anything, it's kind of reassuring, because maybe you don't need a beginning to feel whole. Maybe existence doesn't need a clock to be meaningful. Maybe what matters isn't when the universe started, but how it holds together right now in this flickering, beautiful mystery you call reality. And if time ever turns sideways, just remember, you were already there. You're balanced now, not upright, but mentally, teetering on the ledge between chaos and clarity. And tonight, we tip you right into the moment when everything could have been anything, and yet somehow wasn't. Tonight you're drifting through a universe in the act of choosing its own laws. Because strange as it sounds, the rules of physics you know, the ones holding your atoms together and keeping your chair disappointingly attached to the floor, weren't always there. They had to start somewhere. Welcome to the weird and wondrous realm of symmetry breaking, the cosmic coin toss that turned possibility into particularity. Let's back up. In the earliest moments after the Big Bang, or bounce or brain slap, depending on which rabbit hole you fell into, the universe was a seething, ultra-hot, incredibly dense soup of energy. No atoms, no forces as we know them, no separation between matter and radiation, just raw, undifferentiated energy humming like an angry microwave. And in this primordial haze, all the fundamental forces may have been unified. Gravity, electromagnetism, the strong and weak nuclear forces, all one thing, a supersymmetrical, ultra-ordered state with perfect balance. No friction, no favourites. The universe hadn't made any decisions yet. But then, as it expanded and cooled, like some moody teenager trying to find itself, things started to break. These breaks weren't shattering, but subtle shifts, like ice forming from water, or soup congealing into mystery leftovers. As the temperature dropped, the forces began to differentiate, each one peeling off like members of a once cohesive band going solo. The universe, it seems, went through a phase of creative differences. This is symmetry breaking, and it's the moment when the universe started to decide what kind of place it was going to be. The symmetry that existed in the early universe was elegant but unstable. Think of a pencil standing perfectly on its tip. In theory, it could stay balanced forever, but in practice, it always falls. And which way it falls, that's random, arbitrary. A tiny fluctuation determines everything that comes next. Our universe is that pencil, having tipped, and we're living in the consequences. Historians still argue whether this early symmetry breaking was purely random or shaped by some deeper, hidden structure. But what's certain is that once the breaks occurred, the laws of physics as we know them locked in. Why does light move at the speed it does? Why do electrons have that exact charge? Why is gravity so weak compared to the strong nuclear force? Because the universe made its choices, and once made, they stuck. This process, oddly enough, is similar to how crystals form. In a liquid, molecules can move freely, but as the temperature drops, they align into fixed positions. The resulting crystal has structure, but also defects, tiny imperfections frozen in place, and those defects, they shape everything that follows. So when the universe cooled and symmetry broke, the resulting crystal of reality may have captured subtle flaws, tiny irregularities that would later blossom into galaxies, black holes, and breakfast cereals. Quirky fact for tonight. There's an idea that the universe underwent several phase transitions as it cooled, like stages in a recipe. First came the separation of the strong force from the electroweak force. Then the electroweak force split into the electromagnetic and weak nuclear forces. Each transition, a fork in the road, each one irreversible. And at every stage, more structure formed, more complexity became possible, but also more limitation. The universe started closing doors. It could no longer be everything. It had to become something. Now here's where it gets unsettling. What if these laws, the ones that govern your daily physics, aren't necessary? What if they're just one possibility among many? A cosmic accident of cooling? This is the heart of the string landscape problem. In string theory, there are potentially 10 to the power of 500 ways to compactify the extra dimensions of space. Each configuration leads to a different set of physical laws. Most of them would produce dead, sterile universes, but a few, maybe just one, could lead to stars, chemistry, life. We don't know why we got this one. Maybe it was random, maybe it was inevitable, or maybe, brace for a callback, it was the only one that could ask why it exists. Enter the anthropic principle. Stage left, still smug. It says, we observe this particular set of laws because this is the one set that lets beings like us emerge and observe anything at all. It's not about why the constants are what they are. It's about how we're only here because they are. An observation bias built into the cosmos. That's one view, but others find it deeply unsatisfying. They want a reason, a rule, a deeper law that explains why the symmetry broke the way it did. Why the vacuum settled into this configuration, why the pencil fell this way. But so far, no dice. And here's the twist. The symmetry breaking that shaped our universe might still be happening. Physicists suspect that vacuum decay could be lurking out there. Right now, we live in what's called a false vacuum, a local minimum of energy that feels stable, but isn't the absolute lowest state. Somewhere out there, a lower energy vacuum might exist. And if a bubble of it forms, it would expand at the speed of light, rewriting the laws of physics as it goes. Yes, it would be instant, undetectable, and completely non-survivable. Sleep well, but hey, maybe that's how this universe began. A bubble forming in a higher energy vacuum, expanding, rewriting, becoming our reality. The laws of physics, the particles, the constants, all crystallized in that moment. In that sense, the beginning wasn't the start of time or matter, but the selection of rules, the freezing of possibility into law. You could think of it like choosing the settings in a video game. The menu appears, you don't remember where it came from, but once you click start, the rules are fixed. You can't change gravity or friction mid-level. You play with what you picked, so here you are, mid-game. Bound by laws you never voted for. Electrons refuse to collapse into protons. Gravity doesn't let you float off your mattress. Light travels at the same speed whether you're racing toward it or running away. And none of this had to be true, it just is. Because the universe made its first moves in a haze of broken symmetry, and now, like melted glass frozen mid-drip, you live in the aftermath. Not in a universe that had to exist, but in the one that happened to win the coin toss. You're drifting now, not just between thoughts, but across the thinnest boundary science dares to sketch. You've passed through radiation echoes, mathematical hallucinations, and the symmetry-breaking tantrums of a young universe. But tonight, you approach the edge, the real one, the point where physics doesn't just struggle, it completely breaks. Tonight you slide softly toward the plank wall. This is the limit, the last decimal place, the point where space, time, energy, and logic collapse into a question mark wearing sunglasses. Let's get technical, just for a second. Before we wrap it in metaphor and whisper it into your sleep, the Planck time is the smallest meaningful unit of time, about 10 to the minus 43 seconds. It's not just small, it's meaningless to talk about anything shorter. The physics we know can't describe what happens at or before this scale. Why? Because at that level, The gravitational field becomes as strong as the quantum forces. You need a full theory of quantum gravity to say anything meaningful, and, spoiler alert, we still don't have one. So when cosmologists say the universe began 13.8 billion years ago, what they really mean is we can model what happened after the first 10 to the minus 43 seconds. Before that, shrug emoji. Some call it the cosmic censorship, others a curtain. But the Planck wall is essentially a no trespassing sign posted on the lawn of existence itself. It doesn't just block your view, it questions whether there is a view to be had. And that makes the idea of a beginning even messier. Was there a before, or was that time zero mark not a real beginning, but just the start of when physics starts working again? Let's explore the possibilities, but gently. You're half asleep after all. First, the singularity. According to classical general relativity, if you rewind the expanding universe far enough, you eventually compress it into a point of infinite density and zero volume. That's the classic Big Bang singularity. But infinite is science code for our equations exploded and we don't know what we're doing. Singularities aren't real places. They're signs that your model has reached its limit. Like if your GPS starts giving you directions inside a volcano, you don't keep driving. You stop and reevaluate. So maybe there never was a true singularity, just a Planck-scale quantum state, dense, chaotic, jittery, and undefined by the normal categories of matter and energy. Something that doesn't behave like a place, or a time, or a thing. Something else. Historians, well, physicists, still argue whether the Planck epoch was a real era, or just a placeholder for our ignorance. Some believe that when we finally merge general relativity with quantum mechanics, we'll get a smooth, understandable description of what happened before that 10 to the minus 43rd second threshold. Others think that asking what came before time is like asking what's above the ceiling of the sky. But what might lie beyond the wall, some say quantum gravity will rescue us. That deep down, space-time is not continuous but discrete. Not smooth like fabric but grainy, like pixels. One such approach is loop quantum gravity, which we'll explore soon. In it, space is made of tiny loops woven into a lattice. Time in this view is not a river, but a series of ticks, like frames in a film reel. No flow, just flickers. If that's true, then the Planck wall might just be the first frame. Not the origin, but the beginning of legibility. Like opening your eyes mid-dream and realizing, this is where the story starts to make sense. Fringe idea of the night. Some physicists believe the universe could have tunneled into existence from nothing via a quantum event. That's right. A particle can tunnel through energy barriers, and maybe the entire cosmos did the same from a timeless quantum state. No need for a cause or a before, just a spontaneous transition from nothing to something. And by nothing, we don't mean empty space. We mean no space, no time, no before. A total absence of anything from which everything emerges. Which brings us to our final, most honest answer. We don't know, and not in a lazy way. In a deeply structured, mathematically documented, Nobel Prize validated way. The Planck wall isn't just where our understanding ends. It's where we suspect a whole new kind of understanding is required. A logic that's not just more advanced, but different. Still, you can imagine it, if only metaphorically. A foaming, flickering moment, smaller than anything you've ever imagined, in which all the rules we live by were still trying to figure out whether they existed. A moment where up wasn't up, particles weren't particles, and time hadn't started ticking. A place where becoming was happening, but being hadn't caught up yet. So what do we do with that? We accept it. We let the edge be the edge. Because maybe the true wonder of the beginning isn't in explaining it, but in approaching it, in inching closer, in realizing that, for all our math and metaphors, there's still a place in the universe where the answer is not yet. And maybe that's okay, because in the absence of certainty, wonder survives. And now, as you drift, we slow things down. Not just the words, but the concepts. We fold them back into silence. Let's leave the Planck wall behind. Let's ease the mind from infinite density back into softness. Let's wind down. The light around you fades to a dim, restful glow. The weight of unanswered questions lifts. You're no longer peering into the furnace of beginnings, but floating gently away from it. Carried by curiosity, but no longer pulled by urgency. The noise of particles, equations, and paradoxes falls away, like static settling into a hum. You're a moment now, breathing calmly inside the story you don't have to finish. You don't need the answers tonight. You just need the comfort of wondering. Your breath steadies. Your thoughts loosen their grip. Time may not be real. Beginnings may be illusions. But you are here, quiet, whole, safe. Let the universe keep its secrets. You've earned your rest. You're moving forward again now, not briskly, not with purpose, but like a lazy ripple riding out the last stretch of a wave. You've passed through the cosmic curtain, glanced at the plank wall, and softened into the unknowable. But the universe wasn't finished that day, not even close. Because whatever triggered the universe's beginning, be it a bang, a bounce, or a brain-fueled hiccup, it wasn't just a one-time pop. Tonight, you're floating into something even stranger. The universe, it turns out, started twice. Let that sink in just for a second. There was the moment you think of as the Big Bang, that wild, dense, hot origin point. But that might not have been the real kickoff. According to most cosmologists today, that moment wasn't actually the universe's birth, but more like its second act. The real curtain raiser, that came a few milliseconds later. Welcome to the world of inflation theory, the idea that the universe didn't just expand, it exploded with expansion. For a fraction of a second, the cosmos grew exponentially, faster than the speed of light, blowing up in scale by a factor of at least 10 to the 26th power. That's a one followed by 26 zeros, more growth than your houseplants will ever see. This process didn't make more matter, it made space, a whole lot of it, in almost no time. The first start was the original burst of existence, the Planck scale haze where nothing made sense. But the second start, inflation, was when the universe began to look like something we could eventually recognize, smooth, vast, and eerily even. That's when the stage was really set. And oddly, inflation solved some problems the Big Bang couldn't. Let's rewind for a moment. Before inflation became part of the standard cosmological toolkit, physicists were puzzled by a few things. First, the horizon problem. Why is the universe so uniform in temperature, even in areas that should never have been in contact with each other? Inflation says, easy. Before the rapid expansion, everything was in contact. It was so tiny, so compact, that all the bits could equalize. Then it blew up faster than light could travel, freezing that smoothness into place. Next problem, flatness. The geometry of the universe is very, very close to perfectly flat, not curved like a sphere, not warped like a saddle. That's suspiciously precise. Inflation smooths out any initial curvature the way you might stretch a crumpled napkin until it looks flat. No miracle needed. And finally, the monopole problem. Theoretical physics once predicted heavy magnetic monopoles should exist everywhere, yet we've never seen even one. Inflation fixes that too. It dilutes them. Like adding one drop of paint to an ocean, it spreads any exotic relics so thin, they basically vanish. So inflation not only supercharged the universe's size, it papered over the initial chaos. But it gets even weirder. Inflation wasn't just fast, it was quantum. That means the fields driving it didn't behave like neat and tidy classical forces. They fluctuated, randomly. And those quantum jitters, tiny ripples in the inflation field, got stretched out across the universe. Those ripples, they became the seeds of galaxies. Yes. The reason stars and planets and space whales exist is because of little quantum bumps in an inflating field. The entire large-scale structure of the universe was sketched by noise. So if you've ever felt like your life was shaped by randomness, good news, so was the cosmos. Historians still argue whether inflation is a description or a placeholder, a beautiful idea that works, or a complex patch on a deeper unknown. But so far it explains the data very well. In fact, the fluctuations inflation predicts match beautifully with what we see in the cosmic microwave background. The tiny temperature variations, those little patches of hot and cold scattered across the sky, that's inflation whispering across time, fringe idea of the night. Some versions of inflation suggest it's not a one-and-done event, but eternal. That's right, inflation might still be happening. Not here, but out there, beyond our observable bubble. Pockets of space might keep inflating forever, creating endless new universes. Our universe, in this view, is just one bubble in a vast foaming multiverse. So not only did our universe start twice, it might be one of infinite second starts. And this brings us back to a curious thought. What we call the Big Bang may not have been the most important part of our cosmic origin. It was the noisy, dramatic opening scene. But the real action, the plot twist, was inflation. That's where the shape of the cosmos was decided, where randomness became structure, where possibility narrowed into pattern. It's a bit like baking. The mixing of ingredients is chaotic, unpredictable. But the moment the dough goes into the oven, that's inflation. That's when the shape gets locked. The expansion sets the form. Everything after that is just cooling and decoration. So you might say, the Big Bang was the cosmic mixing bowl, inflation was the baking, and we're the frosting. Unstable, sweet, and not entirely necessary, but delightful nonetheless. Here's one last quirky twist. The field that drove inflation, called the inflaton, has never been directly detected. We don't know what it was, or even if it really existed. It's a theoretical construct, but one that fits the observations with eerie precision. Like a ghost that keeps leaving perfect footprints. So here you are, lying in a universe that started twice. First as a mystery, then as a miracle of geometry. Both beginnings real, in their own way. Both necessary to get you to this moment. A burst of being, then a breathless inflation, then stars, atoms, podcasts, regret, kisses, algorithms, and whatever that noise was in the fridge. 2 starts, 1 reality. And maybe, if eternal inflation is real, more starts still happening right now. Somewhere, in the foamy, ever-growing backdrop of space, a new pocket is inflating. New quantum bumps are being stretched. New seeds of galaxies are forming. A new universe is blooming. And maybe in a few trillion years someone else will be lying in bed, wondering how their universe began. And maybe, they'll say it started twice too. You're winding deeper now, not just into the early universe but into the gears behind it. Into a realm where even space itself is pixelated, time might tick instead of flow, and reality is built from loops, not lines. Tonight you're not falling through space-time, you're knitting it. Because now we enter the jittery geometric world of loop quantum gravity. Loop what now? Take a breath, you'll like this. Loop quantum gravity, LQG for the acronym SAVI, is one of the most promising attempts to unify general relativity with quantum mechanics. A way to describe gravity not as a smooth bend in space-time like Einstein taught us, but as a quantized structure. Discrete, chunky, granular. Like space was made of Lego bricks, not silly putty. Let's rewind for a second. Einstein's general relativity is a masterpiece of smoothness. Space-time curves gently under the influence of mass and energy, and that curvature is gravity. It works brilliantly on large scales. Planets, stars, galaxies. It got us GPS, black hole predictions, and the warm satisfaction of being correct for over a century. But zoom into the quantum realm and relativity stumbles. At small enough scales, near the Planck length, about 10 to the negative 35th meters, the smoothness breaks down. It's like looking too close at a painting and realizing the brushstrokes are fighting each other. That's where LQG comes in. Instead of trying to force quantum rules onto curved space, LQG starts by assuming that space-time itself is quantum. It proposes that the fabric of space is made of tiny loops, spin networks, that interconnect to form a fine-grained web. These loops aren't sitting in space, they are space. Imagine if everything around you, the air, the floor, the awkward mug on your nightstand, was built not from atoms floating in empty space, but from space that itself is made of little chunks. Like Minecraft, but with more math and fewer exploding sheep. The genius of LQG is that it quantizes geometry. That means things like area and volume come in discrete units. You can't have any old size of space, you get specific indivisible bits. Think, pixels on a screen, except your screen is the entire cosmos, and the resolution is absolutely insane. Quirky detail. This idea means that at the smallest level you can't divide space infinitely. No matter how tiny your ruler gets, you'll eventually hit a Planck wall, a fundamental grain of space-time that refuses to split. Space isn't a continuum, it's stitched. So why does this matter? Because when you apply this framework to the earliest moments of the universe, something wonderful happens. Remember that dreaded singularity at the heart of the classical Big Bang? That nasty, infinitely dense point where physics goes to cry in the corner? Loop quantum gravity might remove it entirely. In LQG-based cosmology, Called loop quantum cosmology, or LQC, the universe doesn't begin from a singularity. Instead, it bounces. That's right. Instead of a bang, you get a bounce from a previous contracting phase. Picture the universe shrinking, collapsing down to an incredibly small but still finite volume. Not infinite density, not zero volume, just extremely tiny. Then quantum gravitational effects kick in. Things get weird. Pressure goes negative and the collapse rebounds. Like a trampoline, or a rubber band snapping back, or you trying to get out of a beanbag chair and failing gracefully. Historians, meaning very tired physicists, still debate whether this bounce is the same as previous cyclic models we've talked about. But LQC gives it teeth. It's a concrete mechanism, not just a poetic loop, but a mathematical one. The quantum loops literally prevent the singularity. In this view, our universe didn't emerge from nothing. It transitioned from a previous phase. And just as inflation gave us the large-scale smoothness we observe today, the quantum bounce gives us a natural starting condition. Fringe idea of the night. Some models go even further and suggest that the before and after of the bounce are mirror images of each other, that our universe may have a time-reversed twin expanding on the other side of the bounce. Same physics, opposite arrow of time. So somewhere out there, if you believe time can be flipped like a pancake, there might be another version of the universe where entropy runs backward and people unage into infants. Let's hope they're not wearing backwards pants. But even if we ignore the mirrored twin idea, LQC still offers something remarkable. A finite, consistent model of the universe's beginning without the mess of a singularity. It says the universe didn't just begin, it rebounded. From what? We don't fully know, but the structure gives us something rare in early universe models: predictive power. In fact, some researchers are trying to identify observational signatures of a quantum bounce in the cosmic microwave background. Tiny imprints, anomalies, or deviations that might suggest a pre-bounce phase. It's early work, but if detected, it could turn the bounce from an idea into a revolution. So where does this leave us? Well, in LQG, space is not an empty container. It's a quantum object, and beginnings are not hard stops, they're transitions. You don't need an edge to fall off, just a curve to turn around. Time may still emerge, geometry may still crystallize, but the singularity, gone. And the math, solid. It's not the final theory. LQG has its critics. It struggles to incorporate some of the messier parts of particle physics, but it's a genuine, testable attempt to go deeper than relativity alone. A map of the basement beneath the laws of physics. And for you, tucked in under blankets made of atoms, made of space, made of loops, it's a gentle reminder that even the most violent cosmic events might have softness underneath. The universe didn't explode into being, it rebounded. Not from nothing, but from something else. And maybe that's how beginnings always work, not from absence, but from motion, not from void, but from memory, a loop, a bounce, a breath, and you, here to witness it. You're exhaling now, not just your breath, but your grip on what's real. Because tonight the universe might not be a bounce, or a brane, or a block. It might be a bug. That's right. Tonight you're sliding into the unsettling glow of pixels, patterns, and paradoxes. You're stepping behind the curtain, past the physics, into the code, because there's a theory out there, whispered at the fringes of science and philosophy, that says the universe may not be real in the way you think it is. You might be living in a simulation. Go ahead. Groan. We've all seen the memes. We live in a simulation, mutters the guy spilling coffee on his keyboard. But under the jokes and half-remembered Matrix quotes lies a serious question. What if reality is computational? Let's break it down. This idea isn't about robots or red pills, it's about information. Digital physics proposes that the universe is, at its deepest level, not made of stuff, but of bits. Ones and zeros. Binary code. Everything, matter, energy, even space and time, could be emergent from patterns of information processing. You're not a sack of atoms, you're a data structure. And reality isn't a continuous analog movie, it's more like a very high-resolution video game, running on a processor so powerful you'll never detect the lag. Sound crazy? Let's talk credentials. This idea was notably sharpened by philosopher Nick Bostrom, who formulated the now famous simulation argument. It goes like this. If any advanced civilization, anywhere, ever develops the capacity to simulate universes indistinguishable from their own. And if they run even one such simulation, then the number of simulated minds will vastly outnumber real ones. Which means the odds are you're not the original. Historians still argue whether this is a meaningful probability or just philosophical hot air, but Bostrom's logic is crisp. Either 1. No civilization ever reaches that level of tech. 2. They do, but don't bother simulating us. Or 3. We're in 1. And right now, there's no data that eliminates 3. In fact, some physicists wonder if we might be able to detect the simulation, not with a giant wrench or by pressing escape, but by looking for digital artifacts in the structure of the universe. If reality is simulated, it might have a maximum resolution, a pixel size. That's not absurd. Quantum mechanics already tells us that certain quantities, like energy levels, come in discrete steps. Space-time, as loop quantum gravity suggested, might already be quantized. If space comes in chunks and time ticks like a processor clock, then maybe we're already looking at a cosmic hard drive. One proposed clue, the Planck scale. Remember that tiny length we mentioned before? The Planck length might be the universe's smallest possible unit of space. You can't measure anything smaller. You can't even meaningfully define anything smaller. It's a hard limit. Why would a continuous, infinite universe need a minimum resolution? Well, a simulated one would. Another clue? The speed of light. In a simulation, the processor can only do so much per cycle. Having a speed limit for information might not just be a weird quirk of electromagnetism. It could be the frame rate. Even quantum randomness, that annoying twitch in every electron spin, might be the result of a pseudo-random algorithm, like a cosmic RNG, random number generator spitting out dice rolls. We can't prove it yet, but people are looking, literally. There have been actual experiments proposed to look for grid-like structures in the cosmic ray spectrum, tiny anisotropies that might suggest a lattice behind space itself, like finding the mesh beneath the texture in a game engine. And then there's the most disturbing version of the simulation hypothesis, the idea that the universe might not be just a simulation, but an accident, a glitch, a boot-up anomaly in a larger system. Maybe someone, or something, ran an experiment that accidentally spun out a stable bubble of space-time, like forgetting you left a batch of sourdough starter in the back of the fridge and coming back to find it made sentient bagels. Fringe theory of the night? Some researchers have speculated that black holes might create baby universes, and if advanced civilizations evolve inside those babies, they might intentionally design the laws of physics to maximize black hole production. Why? Because it increases the chance of their own cosmic lineage surviving. This is known, delightfully, as cosmological natural selection. Universes that produce black holes reproduce more, and simulated ones might outnumber real ones. Evolution, but for space-time. Now let's pull back a little, because even if the simulation hypothesis is true, even if we're all running on some interdimensional server rack somewhere, it doesn't change your experience. You feel real. Your pain is real. Your memories are real, even if they were generated by a background process in someone's debug mode. If anything, this theory just reframes the big question. Instead of, how did the universe begin? You now ask, why was it programmed this way? Maybe the laws of physics aren't universal truths but design choices. Maybe the constants we see, the speed of light, the strength of gravity, the charge of an electron, were selected for stability, or curiosity, or aesthetics. Maybe the beginning of the universe was not a burst of matter, but the moment someone hit compile. Or maybe no one did. Maybe the system wrote itself, an autocatalytic loop, booting up from a seed of logic, spitting out time and space as side effects of basic arithmetic. Would that be so different from a bang? Think of Conway's Game of Life, a cellular automaton where simple rules on a grid create patterns that move, replicate, and evolve. From nothing but logic, complexity emerges. Maybe our universe is the game of life with better shaders, and maybe that's okay, because whether or not you're simulated, you're still experiencing, still wondering, still lying here, blinking up at the ceiling like it's a sky you almost remember. And in this moment, the question isn't whether it's real. The question is it beautiful? If you can marvel at the sunrise, laugh at absurdity, and feel awe at the impossible scale of what you might be part of, then simulated or not, it's working, so rest easy. Maybe you're a glitch, maybe you're code, maybe the universe started when a program ran for the first time and it never stopped. And maybe the reason you can even ask that question is the whole point. You're balanced on a tightrope now, stretched between the precision of physics and the fuzziness of fate. You've passed through loops and glitches, quantum bounces and cosmic servers. But tonight, the universe feels almost too perfect. Suspiciously so, like a hotel room with fresh towels, ideal lighting, and exactly the right number of coat hangers. Not too many, not too few, just right. Tonight we tiptoe into the eerie calm of cosmic coincidences. Why do the numbers that define the universe seem so absurdly, implausibly tuned for life? This isn't just philosophical musing, it's one of the biggest mysteries in cosmology. The fundamental constants of nature, things like the gravitational constant, the strength of the electromagnetic force, the masses of elementary particles, aren't arbitrary digits. They are precise, like the settings on a very touchy soundboard. Change any of them just a little, and, well, poof. No stars, no atoms, no chemistry, no you. Take gravity. If it were slightly weaker, matter wouldn't clump. No stars, no galaxies. If it were slightly stronger, everything would collapse back in on itself. The balance is so tight, it's like threading a needle blindfolded underwater while being chased by a neutrino. And the electromagnetic force. Same story. Too strong, and electrons wouldn't orbit nuclei. They'd stick so tightly chemistry would be impossible. Too weak, and atoms would fall apart like discount furniture. Then there's the cosmological constant, the parameter that controls how fast the universe expands. Observations tell us it's incredibly small, but if it were just a teensy bit larger, the universe would have torn itself apart before galaxies ever formed. And the masses of the quarks? Same deal. If the top quark were just a bit heavier, the whole balance of forces breaks. If the Higgs field's value were slightly different, the structure of matter would melt down. The parameters that give particles mass seem tailored, not just for stability, but for us. This strange convergence is what physicists call fine-tuning, and it makes people itchy. Historians still argue whether fine-tuning is a genuine scientific problem or just an illusion created by limited imagination. But many agree. The numbers seem too precise to be random. So where does that leave us? Enter the anthropic principle. It's the philosophical umbrella that says, of course the universe looks fine-tuned for life. If it wasn't, you wouldn't be here to notice. In other words, you can't observe a universe that doesn't allow observers. It's a bit like waking up in a universe where air is breathable and gravity doesn't crush you and thinking, wow, how lucky. But the only reason you can think that at all is because the conditions already allowed you to exist. Is that an explanation, or a cosmic shrug? Some scientists embrace it as the best we've got. Others hate it with the fire of 1,000 suns, calling it unscientific, lazy, or even tautological. You can't test it. You can't falsify it. It's the ultimate because I said so. And yet, the fine-tuning won't go away. So alternative explanations have emerged. One is the multiverse, which you've already cozied up to in Section 9. If there are countless universes, each with different values for the physical constants, then it's not surprising that somewhere, one set of numbers would line up just right for life. And here we are, lottery winners in the grand sweepstakes of existence. Another is cosmological natural selection, hello again, where universes that produce more black holes somehow spawn more offspring universes, making those traits more common. Life isn't the goal here, black holes are, we're just a byproduct of the evolutionary process. And then there are theories of deep necessity. These suggest that maybe the constants aren't tunable. Maybe they have to be what they are, based on some deeper law we haven't found yet. The way the digits of pi aren't arbitrary, they're just what falls out of the math. Under this view, the universe isn't fine-tuned, it's just logical. But we're not there yet. The ultimate theory, sometimes called the theory of everything, still dances on the horizon, elusive, maybe impossible to reach. Fringe idea of the night. Some researchers have proposed that the universe is optimized not for life, but for computational capacity. That is, the physical constants allow not just for existence, but for information processing at maximum efficiency, which makes your brain, your thoughts, and even this bedtime story part of the universe's most efficient data stream. You are, quite literally, the cosmos calculating itself. Let's pause. What does all this fine-tuning say about the beginning? Well, if the universe began with laws and constants already in place, then the nature of that beginning is tied to those settings. Either they were selected, determined, or just happened to be right. And that's the mystery. Was the universe born lucky? Was it filtered by evolution? Was it designed? Or most unsettling of all, was it inevitable? Because if it was inevitable, then all the beauty, structure and meaning we see in the cosmos might just be math unfolding. You didn't win a lottery, you were the lottery. Now let's get cozy with a callback. Remember that cosmic egg from ancient myth? The one that hatched the universe? Maybe the egg didn't just hold the cosmos, maybe it held a rulebook, a set of parameters, a kind of divine settings menu, and maybe when it cracked open, the settings were already dialed to habitable. Maybe the reason your atoms hold together, your lungs breathe air and your neurons spark into thought, is because the universe didn't just start, it aligned. It found a path through the infinite possibilities and walked that line, the tightrope, the razor's edge, and here you are, balanced on it. A universe just right, not too hot, not too cold, not too fast and not too slow, just enough for stars, just enough for chemistry, just enough for you. You're drifting now, not forward, but deeper, into the stillness between ideas, into the soft, inevitable truth that not every question has an answer, or at least not one you get to keep. Tonight, you press your ear to the wall of the universe and hear nothing. Not because it has no story, but because it might be telling it in a language you were never meant to decode. Tonight's question isn't cosmic, it's existential. What if we're just not allowed to know? Let's start with a hard truth. There may be limits to what we can ever observe, not just practically, like we can't build a telescope the size of a galaxy, but fundamentally. The speed of light isn't just fast, it's a boundary. The observable universe is defined by how far light has had time to travel since the Big Bang. That gives us a cosmic horizon beyond which we simply can't see. Not now, not ever. That means we'll never know what lies beyond the edge of our visible bubble. There could be infinite more universe out there. Entire galaxies, physics, events, even other beings. And we'll never see them. Their light will never reach us. Not because we're not smart enough, but because the structure of space-time won't allow it. It's like living in a perfectly soundproof room with no windows. You can theorize what's outside, but you can never hear it, never see it, never test it. And when it comes to the beginning of the universe, this boundary becomes even stricter. Because the earliest light we can see, the cosmic microwave background, comes from a time when the universe was about 380,000 years old. Before that, everything was so hot and dense that photons couldn't travel freely. The universe was opaque. So even though the Big Bang happened around 13.8 billion years ago, we can only see the afterparty. The initial moment itself, the exact conditions, the trigger, the spark, it's permanently hidden. Cosmologists call this the surface of a last scattering, and it's a wall as real as any brick. Try to look before it, and all you get is noise. Historians still argue whether we'll ever find clever ways around this, through neutrino backgrounds, gravitational waves, or mathematical reconstruction. But as of now, there's a hard line between what we know and what we can only imagine. It's a humbling place to stand. Here's a thought experiment for you. Imagine you're a fish in a pond. You can sense the water, maybe the mud, maybe the currents, but you can't see the sky. You don't even know sky is a thing. So you ask, what's above? And the answer never comes. Not because it doesn't exist, but because you're built to swim, not fly. What if we're the fish, trapped in a pond of space-time asking questions that no tool, no telescope, no theory will ever be able to answer? What came before the Big Bang? What started the laws? Why these constants? Why anything? Fringe idea of the night. Some physicists and philosophers toy with the notion of cosmic censorship, the idea that the universe may actively protect certain information from being known, that singularities, like the Big Bang or black holes, are cloaked from observation, keeping their secrets permanently hidden. It's not that the answers don't exist, it's that the universe, by design or by nature, keeps them behind a curtain we can never lift. There's a strange comfort in that, because it means the mystery isn't a flaw, it's a feature. Maybe the universe doesn't want to be solved. Maybe it's not a puzzle, it's a poem, and you're not supposed to finish it. You're supposed to feel it. Quirky thought. Even if we could know, our brains might not be built to understand. A dog can't do algebra. A crow can't comprehend a space shuttle. Not because they're dumb, but because evolution didn't wire them that way. Their worlds are shaped by their needs, and maybe ours is too. Maybe we can describe the early universe but never grasp it. Maybe our language, Our math, our logic, is just a shadow of something deeper, weirder, more abstract than thought itself. Maybe the universe didn't begin, maybe it doesn't need to begin, but we keep forcing it into narrative because that's how our brains survive. Beginning, middle, end, bang, expansion, US. But what if there's only is? And what if we can never truly see past the veil, not because the veil is too thick, but because we are? Now, to be clear, this doesn't mean we give up. Humans never do. We launch probes into the dark. We build colliders under mountains. We teach our machines to think in ways we never could. And maybe, someday, we'll peek a little further behind the curtain. But some part of the mystery will always stay locked. Not in defiance, but in silence. And in that silence, we're left with something rare. Wonder without closure. Not everything needs an answer. Some questions earn their keep by being asked. Think of ancient myths. The cosmic eggs, the world trees, the turtles. They weren't wrong. They were reaching like us into the void. And in some ways, they understood what we keep forgetting. Sometimes the not knowing is the point. Because if we could know everything, would we still look up? Would we still wonder? Would we still dream? Here's a callback to that cosmic baby picture. The microwave background, the smooth glow from the early days of time. It whispers to us across billions of years, but it doesn't explain itself. It just is. Gentle, uniform, patient. And maybe that's the lesson. The universe doesn't owe us a story. We're lucky it left us any clues at all. So tonight, as you nestle into your pillow, let the silence be a kind of answer. Not an end, but a resting point. The mystery remains, and in the quiet between stars, so do you. You're hovering now, not above Earth, not above the universe, but above the very question itself. Not looking for answers, but interrogating the act of asking. Because after all the bangs and bounces, the strings, loops, branes, and quantum burps, what if the real confusion isn't about how the universe began? What if the problem is the word beginning itself? Tonight you pull back even farther, outside the story's timeline, past the chapters and prologues, and ask the question behind the question. Does it even make sense to ask how the universe began? It's a spicy one. Let's start simple. What does beginning mean? To you, it's intuitive. Things start. Stories have first pages. Lives have first breaths. The microwave has a beep. But these are all things that exist in time, and we've already explored the unsettling possibility that time might not be fundamental. So when you say, what came before the universe? You're assuming that time already existed to hold a before and after. But if time started with the universe, as many physicists believe, then the word before becomes meaningless. Not poetic, not mysterious, just linguistically cursed, like asking what's further east than east. Stephen Hawking, ever the cosmic mic dropper, famously put it this way. Asking what came before the Big Bang is like asking what is north of the North Pole. It's not that there's something hidden there. There's just no there there. This feels unsatisfying. Your mind wants a cause, a kickoff, a previously on reality. But if time itself is a product of the universe, then the universe doesn't happen in time. It creates it. Which means the beginning isn't a point in a pre-existing timeline. It's the boundary of time. Think of a book that starts on page 1, not because someone tore out the earlier pages, but because page 1 is where the paper begins. You don't ask what chapter came before the book was printed. Still, the question lingers. Your mind refuses to let go. Because beginning isn't just a time word. It's a causal word. It assumes something made the universe. Something triggered it, caused it, birthed it into being. So let's flip the question. Does everything need a cause? In your everyday world? Yes. Things fall over for a reason. Your coffee goes cold because thermodynamics is a relentless beast. But on the quantum scale, not everything plays fair. Particles pop into existence seemingly without cause. Virtual particles emerge from the quantum vacuum all the time, borrowing energy from nothing and disappearing again. This happens constantly. You're technically being bombarded by random nothings all the time, so maybe causality isn't fundamental either. Maybe it's a pattern that emerges at scale, something that makes sense when you have chairs and cereal and calendars, but not when you're zooming in on the quantum foam. Historians still argue whether causality is a built-in rule of the cosmos, or just a statistical artifact. If it's not universal, then maybe the origin of the universe doesn't require a cause. Maybe the universe didn't happen. Maybe it just is. And that's the core of the discomfort. Your mind evolved to survive in a world of cause and effect. Saber-toothed tiger equals run. Fire equals hot. Rain equals wet hair. But the cosmos doesn't care about your instincts. It doesn't owe you a logic that fits into your sleepy little skull. Fringe idea of the night. Some thinkers argue that existence is brute fact, something that simply is, with no explanation. Not because it's hiding the answer, but because some things may not have one. This isn't surrender, it's honesty. You ask, why is there something rather than nothing, and get silence. Not rude silence, not mystery, just the kind of silence you hear when the question might be malformed. Because nothing is itself a concept, a label invented by minds that live in a something. Can we even conceive of true non-being? Or do we just imagine an empty room and remove all the furniture? Maybe nothing was never possible. Maybe existence is the default, and non-existence is the exotic state, the thing that needs explaining. Or maybe the universe is like a mathematical truth, uncreated, uncaused, just there, like the number pi, not something that happens, something that simply is, forever, everywhere, without needing to be built. And maybe trying to understand that in human terms is like trying to hug an idea. Here's a quirky callback. Remember the block universe, where time is a static dimension and all events exist at once? In that model, the universe doesn't begin or end. It just is. Every moment, past, present, future, is baked into the geometry. You're not watching a movie, you're living inside the film reel. So again, the beginning isn't a moment, it's just a location. Like asking, where's the beginning of a mountain? Depends on how you define start. The bottom, the base camp, the tectonic collision 60 million years ago. Maybe you've been asking the wrong kind of question all along, not when did the universe begin, but why do we expect it to have a beginning? Here's a softer thought. Maybe the universe is a self-contained loop, a structure that exists because it can, like a sentence that refers to itself, or a thought that thinks itself into being. In mathematics, these loops exist. Self-referential systems, logical structures that define their own terms. Maybe the cosmos is the ultimate one. Maybe existence is a strange loop, which brings us full circle. You're lying there now, your thoughts spiraling around a question that may never have a satisfying end. But that's okay. Because maybe the universe didn't begin. Maybe the universe doesn't need to make sense. Maybe it just is, and maybe that's enough. You're quiet now. Not because the story is over, but because you've circled back to where it always leads, to yourself. Not to ego or certainty or some triumphant revelation, but to the gentle, flickering question at the heart of all this cosmic noise. Why are you even asking? You've travelled far tonight, through loops, fields, equations, myths, membranes and metaphors. You've touched the plank wall and peeked under the universe's hood. You've wrestled with time, causality, and the unsettling idea that your reality might be a simulation, a bubble, or a bug. And yet here you are, still asking, still wondering, still reaching. Maybe that's the real secret the universe keeps whispering in every background hum and ripple of starlight. Not about how it began, but about why it matters to you. Because here's the quiet truth. You are the universe. Not metaphorically, not spiritually, literally. Your body is made of elements forged in stars. Your atoms once floated in deep space, scattered by supernovae, swirled into clouds, pressed into rocks, breathed by trees, recycled through oceans, eventually reassembled into a bipedal ape with insomnia and an internet connection. You're stardust with curiosity, a lump of carbon that woke up and started asking why. You're not an outside observer, you're not standing apart from the universe, taking notes like a tourist at the edge of existence. You are existence, briefly organized into a pattern that can ask questions about itself. You are the universe, asking why it exists. That's not just poetic. That's what happens when atoms gain enough complexity to model reality. Consciousness isn't some add-on, it's what matter does when it gets interesting. So when you ask, did the universe have a beginning? The real question is, what kind of universe produces creatures that ask that? The answer is, this one. Whether it began with a bang, a bounce, a field, a code, or never began at all, it ended up producing you. You, listening quietly, eyes half closed, drifting through questions as old as breath. And the most extraordinary thing? You didn't have to be here. The odds were stacked against it. Against stars, against life, against the emergence of language, culture, curiosity, late-night science videos, and the human need to know. And yet, you made it. Somehow, this flickering soup of laws and loops produced a conscious moment. This moment, right now, historians, physicists, philosophers, they still argue, they always will, about beginnings, boundaries, causes, and constants. But the deeper we go, the more the lines blur, the more you realize the universe may never answer. Because the act of asking might be the real miracle, and maybe that's enough. Maybe the point isn't to solve the riddle, but to keep listening, keep wondering, keep making meaning in a universe that doesn't hand it to you. Because whether the cosmos is eternal or brief, cyclical or simulated, divinely coded or randomly assembled, you're in it, you are it. So rest easy, Stardust. You've looked backward far enough for one night. Time will keep moving, or not. Galaxies will keep spinning, or dissolve. The constants will stay constant, or shift with some grand equation we haven't written yet. And you'll close your eyes and slip gently into the dark. Not because you found the answer, but because you found yourself in the question, and that somehow is even better.